So let's begin section 1.4. So this is section 1.4 on matrix equations. In the last section, we talked about vectors. Now we're going to start talking about matrices again. So let's begin with a definition. If A is an M by N matrix, columns A1 to AN, and if X is in Rn, then the product of A and X, denoted by AX, is the linear combination of the columns of A using the corresponding entries in X as weights. That is, it's a lot of complicated stuff. You have the AX equals, you could write it as a product, you could write it as a matrix times a vector, or you could write it as a linear combination. AX is only defined if the number of columns of A equals the number of entries in X. So let's play with this so you can see what's going on. So I want to calculate the product AX equals B. And so my matrix that I'm going to work with is 1, 2, 3, 4, 5, 6. And then I have -1, 0, 2. Just a note about my own notes. I will try to use vectors and matrices like 1, 2, 3, 4, 5, 6 as often as I can, so that you can easily catch the pattern and write them down. They're not exciting, but you don't want to have to be like, well, what was that entry, where it's not necessary. So this can be written as -1 times 1, 4 plus 0 times 2, 5 plus 2 times 3, 6. So notice that the columns of the matrix A are showing up here, and the entries of vector X are the weights in our linear combination. Here's our A, and here's our X. Everybody okay with multiplying matrices? In this case, we're doing our matrix multiplication by thinking about our product as creating a linear combination. Linear combination. The columns of A. Next example, same thing. So I have 1, 2, 3, 4, 5, 6. Now I'm running down the columns, and I want to point out that the number of columns in the first matrix has to match the number of rows in the second matrix or in the vector. So this would be the same thing as -1 times 1, 2, 3 plus 2 times 4, 5, 6. Notice once again that the column vectors in A are showing up here, and those we're going to have a linear combination of those columns as dictated by the vector X. Here's your A, and here's your X. Eight, 10, and 12. I've got 7, 8, 9 for my answer. In the original equation, AX equals B, we're saying that this bit right here at the end, the 7, 8, 9, that's our B vector. From Ahmed, his question is A here augmented? So in this particular case, A is not augmented. If we were going to augment it, we would write it as A augmented with B. We're messing around with this idea of a matrix equation. That's our concept that we're working on. And so what we're trying to do is learn different ways of writing the same thing, or different representations of the same thing. So first of all, in example 2, for U1, U2, U3 in, what should go in the box here? What goes in the box? An R. Thank you, Felix. R3, write the linear combination of 5U1 minus U2 plus 2U3 as a matrix times a vector. So to do this, so I have 5U1 minus U2 plus 2u3, 2u3. And what I want to point out is that you have a bunch of vectors here, and with coefficients 5, -1, and 2. And so you could write this as the matrix U1, U2, U3, where these guys are column vectors. And I'm going to do the little lines above and below to help you remember that those are columns, times 5, -1, and 2. So in the next example, where we're looking at the system, what we're going to do is we're going to try to write the same thing 3 different ways. So you can sort of see different representation. So I want to write the system of equations 3x1 minus x2 minus 4x3 equals 3, and x1 minus 5x3 equals -2 as a vector equation, as a matrix equation, and as an augmented matrix. So the first thing I'm going to do is I'm going to write it as a vector equation. So this is saying we have how much, here's my x1s. How much x1 do we have? Looks like we've got 3 in the first equation, 1 in the second, plus how much x2? Looks like we've got -1 in the first equation and 0 in the second. And then how much x3? -4 in the first, -5 in the second. And this is going to be equal to 3 minus 2. So this right here is going to be property number 5 on the next page. So that's if it's a vector equation. That's what we did yesterday. So next, I want to write this as a matrix equation. This is more like what we were just doing earlier. And so we would write it as 3, 1, minus 1, 0, minus 4, minus 5, times x1, x2, x3. And this will be equal to 3, -2. So this is the AX equals. So lastly, we could write the same thing as an augmented matrix. So you could have 3, 1, minus 1, 0, minus 4, minus 5, 3, -2, augmented matrix. So here you've got the A augmented with B. Here you have AX equals B, and here you had like x1, I don't know how we want to write this, v1 plus plus x3 v3 equals b. And so this is property number 4, and the last one is property number 6. Theorem 3 says that if A is an M by N matrix with columns A1 to AN, and if B is in Rm, the matrix equation AX equals B. Here's our property number 1. Where's our property 4 that we used yesterday? So this is the property 4 that we referred to yesterday. So the matrix equation would be AX equals B, has the same solution. So here's the matrix equation version. Matrix equation has the same solution as the vector equation, which would be this one, which has the same solution as the system of linear equations with the augmented matrix, which would be this one right here. Okay, so they all have the same solution. It's just different representations of the same thing. And so we will say that the equation AX equals B has a solution if and only if B is a linear combination of the columns of A. There's like multiple ways of saying saying things, but that's definitely one of them. All right, so let's look at an example. So let A equal this matrix and B be an arbitrary matrix or vector B, B1, B2, B3. And so I want to know, is the equation AX equals B consistent for all possible B1, B2, B3? Short answer, no. Long answer, if we want to know when something is consistent, we're looking at consistent, then what we want to do is we want to row reduce, and we want to look for a row that for 0, 0, and then we want there to be a 1. And if you end up with this 0, 0, 0, 0, 0, 1, this would tell you that it was inconsistent. And so we're going to try to keep our eyes on that. So what we're going to do is we're going to start by setting up an augmented matrix. So let's make sure you're tracking what's going on. So A is giving me the columns on the left of the augmented matrix, and then B here is this part of the augmented matrix. So now we need to row reduce. As soon as you see letters in, thanks for the suggestion, Kyle, I'll try that after class. As soon as you see letters in what you're trying to row reduce, that's a hint that we're going to need to row reduce by hand. So if we want to get rid of the, if I want to get rid of the, apparently everything. Oh my gosh, Dust. Apparently I'm excited about a new president or something. -3 and 5. Okay, so if I want to get rid of this -3, then what I can, and I already have a pivot, a 1 in my first pivot position, I can take row 2 and I can add opposite sign of the -3, 3 of row 1. That's my pivot, and that'll become my new row 2. So those are kind of my method for the madness. And then here I've got a 5. And so to deal with the 5, I'll have row 3 minus, so it's the opposite sign, 5 row 1 is going to become my new row 3. So just kind of reminding you of that process. You erased 8 in row 3. Oh, nice. Thank you for that. Super funny. All right, so then that changes our matrix. So our new updated matrix, the first row stays the same. The second row becomes 0, -7, -6. And then B2 plus 3B1. And then the third row becomes 5 or 0, 14, 12, B3 minus 5B1. Okay. So yay. Now we have a 0 and a 0. So we're just trying to figure out whether this thing is consistent. And in the first case, we were taking advantage of the pivot in the 1-1 position. And now you can already see that we've got a pivot in that 2-2 spot. And all we really care about is knowing whether it's consistent. So I don't need to divide by 7. I can just save myself a little bit of writing. So let's see. So if we want to get rid of this 14, we can take row 3 and add 2, row 2, make that our new row 3. And so again, that's 14 plus 2 times -7. That's why that's why we're able to do this. So good news, things work out nicely. So then we're going to get 0, -7, -6, b2 plus 3b1, and then 0, 0, 0, b3 plus 2b2 plus b1. And so going back, like, what are we trying to figure out? Our question is the system consistent? Is it consistent for all b1, b2, b3? So in order to be consistent, so it's consistent if this quantity right here, which is b3 plus 2b2 plus b1 equals 0. Let's check. The question is this always consistent? Always a solution? I've got some no's, and I got lots of no's. So the answer is it's definitely, there's not always a solution. And the reason there isn't always a solution is because you're only going to get a solution if things happen to work out just right. Questions about this example? Theorem 4, next theorem, says in case you're wondering where these numbers come from, these are from the text. That's the numbering is lining up with the text here. So let A be an M by N matrix. Remind me, is M the number of rows or the number of columns? M is the number of rows. N is the number of columns. Okay. So if A is an M by N matrix, then the following statements are logically equivalent. They're all true statements or they're all false. So for each B in Rm, the equation AX equals B has a solution. Each B in Rm is a linear combination of the columns of A, and the columns of A span Rm. So these are equivalent statements, are all true or all false. And you will find a number of these like equivalency statements in this class where we'll say, here's 3 things, or here's 5 things, or in one case, it's like, here's 10 statements that these 10 statements all mean the same thing. And so you just have to sort of get used to that. I think you're already used to it in some ways. I mean, it's like an aside. Think about how you're used to saying, "Oh my gosh, that dead part of the screen." You're saying that 1 is equal to 2 over 2, right? Those are equivalent things. You can go back and forth. Or you're used to the fact that like x squared minus 1 is equal to x plus 1 times x minus 1. So you're used to this in an algebraic sense. Now we're doing it sort of in a logic sense. Okay. So let's add a couple things here. So I think it's these, the C and the D are the hard ones. So let's spend a little bit of time on C and D. And in order to do that, we need some new notation. So our new notation is, we have an upside down capital A. And an upside down capital A means for all. And we have a backwards capital E. And the backwards capital E means there exists. So we'll find ourselves using this notation for shortcuts in this class. So when we say that the columns of A span Rm, what we're saying is that for all V vectors in Rm, there are scalars or weights sorry, scalars C1 to Cn, C1 to Cn, such that C1 A1 plus Cn An equals V, where A is equal to A1 to An. Okay. So the A1 to An, those are the columns of matrix A. And so we're saying that for every vector in Rm, we can make it from a linear combination of the columns of A. So that's what that C part is telling us. So then if in D, when it says that A has a pivot position in every row, it's saying that if we row reduce, you're going to have all those pivots. And you're never going to have no pivot. No pivot would mean you would have, what would it look like if there's no pivot? I think you could have free. I think you can have free variables. I think it means you're never going to have the 0, 0, 1. Oh no, never 0, 0, 0, 0, 0. So I gotta think for a second. Yeah. So you won't have any 0. You won't have any 0 rows. Okay. I gotta think. Double check my own brain. Yeah. Okay. So a key to all this stuff is that this A is a coefficient matrix. It's not an augmented matrix. So that's why I don't have the equals 1 on the end. So it's a coefficient matrix. Okay. Questions, comments?
Does that mean that you can only have a unique solution?
Say that again.
If you're not going to get 0, 0, 0s, you're going to get only one solution, right?
One solution. If we span, I could get free variables. Not necessarily. So I had to Good question. I'm like, that the way you asked it helped me figure out what I was struggling with. So imagine you had a pen that worked. So imagine you had something like 1, 2, 0, 0, 0, 0, 1. Maybe I'll do a, come on, 3 and 4. So notice in this particular case, you have pivots in every row, just like it was saying, but you do have free variables. So you won't necessarily have a unique solution. Does that make sense, Adis?
Yes, thank you.
Yeah, thank you for asking that, because I was like, there's something about this that I'm not explaining clearly, and the way you asked it helped me to pull that together. So I appreciate that. Other questions? Very good. All right, so let's look at example 5. So in example 5, we want to compute AX equals B for A equal to this given matrix and X equal to the vector X1, X2, X3. And so remember that you can take that AX and you can think about this X as giving you the weights of the columns. So we could write this as X1 times 1 to -3 plus X2 times 4, 0, -2 plus X3 times -1, -3, and 5. Okay. So here's those weights, X1, X2, X3 showing up, and they're the weights of the columns of A. So here's those 3 columns, and so we're weighting the columns like that. And if you wanted, you could bring all this stuff together, and you could write it as a single statement, if you will, like X1 plus 4X2 minus X3, 2X1 minus 3X3 minus 3X1 minus 2X2 plus 5X3. And what we're trying to do is we're trying to compute when this thing is equal to B. And so on the other side, we would have equals B1, B2, B3. Something like that. So we can't, we're not going to get numbers out the other end, because, but this would shows you how we could turn this statement into a system of equations. So AX equals B into system of equations. So we have been talking about matrix multiplication, and we've been doing it kind of by treating things like linear combinations. And now we're going to look at matrix multiplication a second way. So this right here is a second take on matrix multiplication. So in order to do this, think dot product. Is remember your dot product from from other classes where to find the dot product, you take the entries and you multiply them by each other and you add up those products. So what we're going to do is we're going to do basically the dot product of the first row of A and the column of X. So I'll have 1 times 1 plus -2 times 2 plus 3 times 5. And so there's your, oops, come on. So here's the 1, the -2, and the 3. And then the 1, 2, and 5. Okay. And then we'll have 0 times 1 plus 4 times 2 plus -1 times 5. Again, row, let me change colors. Row times column. And all this stuff is equal to 12, 3. So for matrix multiplication, you dot, like it's a dot product, the row and column. The row of the first matrix and the column of the second matrix or vector. So like the yellow one here and the light blue one here. This isn't a dot product. This is the same type of calculation as a dot product. So you could think about this as trying to answer. So Sung-Hoon's question was, how does this dot product relate to this? You could think about this lower entry, for example, as taking the row, the green row, and dotting it with the light blue column. So it's not a dot product in the sense that you're finding an angle or something along those lines, though we will talk about those things later on in this class. But you could think it's more of a calculation tool. So in B, we're going to do the same thing, and we're going to take the first row and we're going to multiply by that first column. And so we're going to get 1 times A plus 0 times B plus 0 times C, which is just A, no parentheses. And then to find the next component, we'll take the second row and we'll again multiply it by ABC. And so you get 0 times A plus 1 times B plus 0 times C, which is just B. And then you take your third row, 0, 0, 1, multiply it by ABC, and 0 times A plus 0 times B plus 1 times C, which would be C. So notice that in this particular case, we have our A matrix and we multiplied by X. X is the ABC. And you get out the same thing that you started with. So it's almost like we multiplied by 1. And so like Gerald said, we're multiplying by 1. And so this matrix over here, 1, 0, 0, 0, 1, 0, 0, 0, 1, is our first example of what's called an identity matrix. And usually we will note it with the letter I. So this is called the identity matrix. If IN represents an n by n identity matrix, then IN x equals x for every, and once again, we get x in Rn. It's like like multiplying by 1. But now with matrices. So Tommy asked, what's the use of an identity matrix? Maybe I could ask the question, what's the use of 1? It's going to get used a whole bunch. It doesn't necessarily have a lot of use in and of itself, but it's going to be used either to tell us things or as an end result or as an intermediate step, just like the number 1 has been throughout so much of our math careers. So good question. Hang on, you're going to see lots and lots of uses of the identity matrix. If you struggle with it, if you struggle with the identity matrix, which frankly, I don't think any of you will, that means you're having an identity crisis. If you find somewhere along the line, you lose points because maybe you didn't write down an identity matrix when you were supposed to, you got it, there was identity theft. So be careful about both of these things. Bad jokes aside, let's look at one more theorem here. And the point of this next bit isn't because it's complicated, it's because I want to give you another example of a proof. It's a nice way to end the class. So if A is an M by N matrix, and U and V are vectors in Rn, and C is a scalar, then we have these two principles that we can distribute. And notice this is left multiplication. So you have A times U plus V is the same as AU plus AV. And then also A times CU equals CAU. And so we want to prove this statement. And specifically, I'm going to work on the second one. So I'm going to prove B. So again, there's those 3 lines that we have right at the top of every proof. So we're going to start by writing our claim. So our claim is basically everything that's above. So it says, if we have our A matrix, which is M by N, U and V, well, I guess I just need U. So U is in Rn, and C, a scalar. Come on, little buddy. Then we're saying that A times CU equals C times AU. Ooh, am I cutting out? Can you hear me? Can people hear me? I got some thumbs up. Okay. So we did our claim. The next line is proof with a period and an underline. The next thing we need to do is we need to define all of our terms. So we got to have a whole bunch of things be given. So notice what we're talking about above here. We've got an A, we've got a U, and we've got a C. So we've got to define all of those things. We got to get them. So we're going to say let A be given, and we're going to, knowing where we're going to go, we're going to write our, I'm going to break out our A into its columns. So let A U, which is equal to U1 to UN, and scalar C okay, so I have to like tell you what they look like, what's the form of them. I think we're going to go a couple minutes long, but we should be able to finish this up pretty quickly. So then the claim is that ACU equals CAU. So we're going to start on the left side and work our way to the right side. So we have that ACU equals A times parenthesis, and then I've got CU, which would be C times U1 to UN. So here on the left side, we can just use our properties of vectors, and we can bring the C into that vector. So this will be equal to all those A's again. Times vector CU1 all the way down to CUN. So now what we recognize is that we can write this in terms of linear combinations. So we're going to use linear combinations. And so this will be equal to CU1 A1 plus dot 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 plus CUN AN. Okay. So to Sammy, no, don't let anybody else in at the moment. Okay. Notice that there's a common factor. Ooh, that didn't work. There's a common factor here of C throughout. So we can pull that factor of C out. And so I have C, and what's left behind is U1 A1 plus dot 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 plus UN AN. Okay. This is again a linear combination. Almost there. So hang with me. And so it's a linear combination, and so we can rewrite it as a product. So we've got C, same C, and now we've got our A matrix all the way to our A, N, and then we're multiplying by the U's. Something like that. And so here you see C times A U. So we can state our conclusion. Therefore, A times CU, not CA, CU equals C times AU.